This is section 8.2, and the title of this section is Impulse Changes Momentum. And the word impulse, you're going to learn what that means very soon. It may not mean what you think it means. So our main idea is the change in momentum depends on the force that acts and the length of the time that that force acts on a mass. The momentum in an object changes, either the mass or the velocity or both change. In most cases, it's going to be the velocity, simply because the mass is not really gain matter. But you can actually move it if you apply a force to it. So if we apply a greater force on an object, we're going to change its velocity, and if we change its velocity, then we're going to change its momentum. And the greater the change in velocity, the greater its change in momentum. So the other part of that is if you push on something for a longer period of time, you're applying more force to it over a longer period of time, and you're going to change the momentum more than if you just apply a force briefly. The more you push on it, if you want to get something moving, you'll push on it for a long time rather than just give it a short push, and that's going to change its velocity. So in this case, what we see is both force and the time that we apply the force are important to changing an object's momentum. So let's look at an example. When you push with the same force or twice the time, you impart twice the impulse and produce twice the change in momentum. So what we're talking about is, now we can actually give a formula to the word impulse. Impulse is the force that you apply to an object by the amount of time you apply it to an object. And the greater the impulse you exert on something, the more you're going to change the momentum. So here's the real definition of impulse. Impulse is really the change in momentum. And we can see that if we take the impulse equation, force times time, and we set it equal to the momentum equation, we have force times time equals change of momentum, which is a change of the mass times the velocity. And like I said, a lot of cases, it's not going to be the mass that's changed, it's going to be the velocity only. And one more thing I want to talk about, if you read right over here, if just like you can have the same momentum if something moves fast, a small object moves fast and a large object moves slow, you can produce the same amount of impulse if you apply a greater force for a short period of time or a smaller force for a longer period of time. And that's really what it's saying right here. Large force over a short period of time, or a small force over a larger period of time. So to increase the momentum of an object, now we want to apply the greatest forces possible for as long as possible. And then you can see I put a golf swing up there. And the reason why I put a golf swing up there is that we're often told when we play sports that we should follow through with your swing or follow through with your throw. And what you're trying to do is impart a force on an object for the longest time possible by following through on your throw. You're trying to keep the golf club in contact with the ball, or the bat in contact with the ball, for as long as possible, so it imparts the most force on it. And as a result of imparting the most force on it, it's going to do the greatest change of momentum, which will lead to the greatest increase in velocity of the ball or the baseball or golf ball or whatever you're trying to change the velocity of. Now, one of the things you got to remember, though, is that you don't just apply one force to a golf ball on a swing. The amount of the impact on the ball, the amount of force on the ball, varies throughout the impact, and the ball itself changes shape, and as it changes to its original shape, it starts to gain more speed. And what you need to do in this case is use the average force, much much like the way we used average speed when we did distance, velocity, and time questions. This is not a huge detail, but just something you should be aware of. So let's say we were going around a corner and we wanted to, we were afraid we were going to lose control of our car and run off the road. You'd want to hit a haystack more than you'd want to hit a concrete wall. And there's a reason why. If you look at this diagram here, you're going to see a car with hitting a haystack, and you're going to see that the haystack actually applies a very small force, but over a long period of time. Therefore, you're going to lead with the force of impact is going to be very small on the car. Conversely, if you hit a brick wall or a concrete wall, it's going to be a very high force over a short period of time, and you're going to have more damage done with a very high force hitting the wall. Now, one thing we don't want to do is we don't want to confuse impact with impulse. Impact is a force. Impulse is the impact force times the time. So, let's say we were to hit a haystack or a wall with the same car moving at the same velocity. They're both going to end up with the same impulse acting on them. But that doesn't mean that it's going to be the same amount of force, the same amount of time. As you can see, the haystack is going to have a smaller amount of force because we've extended the time. And the brick wall is going to have a larger amount of force because our impulse is acted over a very small amount of time. So when you extend the time, you reduce the force. Things like a padded dashboard in a car are safer than a rigid metal one. You guys are probably too young to remember when dashboards were really, really hard and the seatbelts weren't that good. And people used to get killed because they would smash their head into the dashboard. Now you have airbags, and once again, the airbag is providing an impulse to change your momentum. It's just doing it over a long period of time with a very small force, so your face doesn't get that damaged. And you see this in sports. When you go to catch a ball, you extend your hand out and then you give with the ball. You see it with receiving a pass in basketball. You see it with receiving a pass in lacrosse. You see it in receiving a pass in soccer. You name the sport, you almost always give with the ball when you make contact with it in order to make a catch. Now here's a funny photograph of a sumo wrestler falling, and what this has to do with extending the amount of time by using your extremity to cushion. Here's an example. When you jump to the ground, you have to bend your knees when your feet make contact, so it extends the time during when your momentum decreases. If you jump down and lock your knees are going to hurt because there's going to be a large amount of force over a small amount of time. When you bend your knees, it's going to be a smaller amount of force over a longer period of time. Here's the wrestler. The wrestler, you can see, has extended his hand out here to decrease the amount of time of impact. He's also going to roll a little bit too, and that's going to take up some of the force and extend the force out over a longer period of time. So it's going to be a smaller force. Now here we have a boxer moving away from the punch. It's going to have a larger period of time, smaller force. This boxer doesn't move toward the punch. It's going to be a larger force, shorter period of time. What if we were to drop a glass on a sidewalk? It's going to break. But if you drop it on a carpet, it has a chance of not being broken because the carpet has give. When you hit the carpet, the carpet takes longer to slow the glass down, so you're going to have a smaller force. When it lands on a sidewalk, the sidewalk doesn't give, so it's a large amount of force over a very small amount of time, and the glass subsequently may break. Here's a safety net used by circus acrobats. If you don't have a safety net, you're going to hit the hard ground. You're going to stop in a very short amount of time with a very high force. If you land on a safety net, it's going to be increasing the time of the impact, but it's going to be a much smaller impact force. So when a dish falls, will the impulse be less if it lands on a carpet than if it lands on a hard floor? The answer? No. The impulse is going to be the same. What's going to change, though, is the force is going to be less because there's a greater amount of time for the momentum to change. Let's look at a couple other examples. These are crumple zones, which is the area in the front of a car right between the engine and the passenger compartment. Here's a good example of it right there, where the car actually bends and smushes to absorb the impact, and the cars are designed that way to increase the amount of time, which will lower the force on the rest of the car. Here's an impact attenuator. You've seen these mostly at bridge overpasses and near exits. They're usually filled with water or sand, and once again, rather than hitting a concrete wall, you're going to hit water and sand, which is going to give a little bit, and it's going to be a lot less force over a longer period of time to slow you down. And here's a soccer player taking one to the face, and you can see his face is squishing, so it's extending the amount of time. The ball's squishing too to extend the amount of time. Just a great photograph. Now, here's another example of it, and this is true for almost any shoe. It doesn't just have to be Nike or Nike Shox, but the whole idea behind the midsole of a shoe is that it extends the amount of time that your foot is slowing down when your foot hits the ground, therefore lessening the force on the rest of your body, so you can get that jarring feeling. And Nike just came up with these ideas of using air and also sort of a spring system inside their shoes. And the advantages to those two systems are that over the lifetime of a shoe, if the bubbles don't pop or the springs don't break, the midsole of the shoe will last for a long, long time than if it's just this regular foam, which will have a tendency to compress down and not be able to absorb impact as much.